In this video, I'll teach you how to graph a function. Now for an example, I have f of x equals to 2x to the power of 4 minus 4x squared plus 2. It is a polynomial function. And we'll look into all the aspects which we should consider to sketch a neat curve. Now the aspects are, first and foremost, is type of function. So what do we have? What type of function do we have? That is first and foremost thing which we should know. So we know it's a polynomial, right? So we'll write down it is a polynomial. Okay. Now what else you can say about it? It looks like an even degree polynomial, right? It is even degree. It's also even, let me write degree, and which is, of course, degree is 4 in this case, and it's also an even function. How do you know it is even function? F of minus x is equals to f of x, right? Even function because f of minus x is equals to f of x, right? I was not intending to give you all these details, but let's now go through it, right? Now, and then, since it is a polynomial, we can say the end behavior, it is like positive. So end behavior is, let me write down now, end behavior. So end behavior is as x approaches infinity, what will happen to y value? So if x approaches infinity, this is positive leading coefficient. Therefore, y also approaches positive infinity, and as x approaches negative infinity, y also approaches positive infinity, right? So either side, it is like moving upwards, correct? That's the end behavior. Now, can you find the x and y intercepts for this graph? Y-intercept is always easy. So let me write that first. Y-intercept is basically the value of function at 0, x equals to 0, right? That is y-intercept. So f of 0 for us is 2. That's it. Now how about x-intercept? So for x-intercepts, we have to do a lot of work. At times, if it is very difficult, just forget about it, right? Now in this case, it is kind of simple, and therefore we'll go ahead with it. Now to find x-intercept, we should basically factor this, right? So I can write this f of x as equal to, we can factor 2 out. So if I factor 2 out, I get x to the power of 4 minus 2x squared plus 1, right? Now this becomes a perfect square. This is like square of x squared. This is 1 square, and the center term is 2 times ab, right? So we can write this as 2 times x, or rather it's not a perfect square, a square minus 2ab, and this is x square, right? So we can write this as x square minus, this is like minus 1, so minus 1 whole square, oops, minus 1 whole square, yeah. So it's a perfect square. But see, we can further factor this, right? So it becomes 2 times, so this is degree 4, x squared minus 1 could be written as x plus 1 times x minus 1, right? So let me factor this further, and let me write this as x plus 1 squared, because of this square, right? Times x minus 1 squared. So that is how the function is. Now, if we do that kind of a thing, you know exactly how to sketch it, right? So you got a fairly good idea of sketching this one. Now how will calculus come into picture? We'll see that part also. Now from here we know x-intercepts are at x equals to plus and minus 1, and we have double zeros. That means it is going to turn at those points, right? So we can write x-intercepts are at x equals to plus and minus 1. So plus and minus 1 will give me x-intercepts. So let me write it here. These are my x-intercepts, okay. Fine, so we got x-intercepts. Now we know x-intercepts and all this. Let's look into symmetry. So how about the symmetry? As we say, it's an even function, right? That's a symmetry. So we say it's an even function. Yeah, we have already covered that part. And how about asymptotes? Now whenever we are talking about polynomials, we should not be talking about asymptotes. Now these are the functions which are smooth curves from minus infinity to plus infinity, that means domain and range, right? So let's say domain and range, correct. So domain is no restrictions at all. Domain is x belongs to real numbers, that's it. And as far as the range is concerned, they do have a turning point, and at this instance we have a fairly good idea about the range. So we have both the x-intercepts and they're turning from there, so we know fairly well that the range is y belongs to real numbers where y is greater than or equal to 0, right? It's kind of early to put it in. We haven't really sketched the graph. I'll prefer most of the time to plug in range at the end once you've sketched the graph, right? So don't do it, don't hurry for it. But in this case, since this polynomial is very familiar with us, so we'll go ahead. Now that is how you could actually now sketch this graph fairly accurately with the help of your knowledge on advanced functions. Now, how do calculus come into picture? There are two, or rather I should say one critical point left here, and that is to find point of inflection. So with the help of calculus, we'll find point of inflection here, okay? So how do you find point of inflection? So before that, let's find the first derivative, and first derivative gives us maximum, minimum, and also interval of increasing and decreasing. So let's get into that. So that is interval of increasing and decreasing, right? So interval of increasing and decreasing. That is what we are getting into now, and this you get from first derivative, right? So we'll try to figure out first derivative. So let's start with calculus. First derivative. Okay, so we already have a function which is given to us, y f of x equals to 2x to the power of 4 minus 4x squared plus 2, and let's write down its derivative. So we have f dash x equals to 8x cubed, right? 8x cubed and minus 8x, okay, 8x, that is it. And this I could write this as, I can take 8x common. So if I take 8x common, I'm left with x squared minus 1. Correct. And that gives me 2 zeros. So I have two critical points, and my critical points here are critical numbers, let me call. Critical numbers are at x equals to plus minus 1, right? So they are at x equals to plus and minus 1. So these are my critical numbers, correct? Analyzing this part, and then x equals to 0 and also 0, right? So there are three critical numbers for this particular case, correct? Now let's analyze all three of them and see where do we have maximum, where do we have minimum, okay? So I'll just sketch it here itself. So I'm drawing this line, and I have three critical numbers here. One is at x equals to 0. Let us say that this is my x equals to 0. The other two are at plus and minus 1. So let's say this is minus 1 and this is plus 1. I actually took them very close. Anyway, so yeah, I should have spread them, but now what to do? Let's leave it for the now. Okay, so this is 0 for us, and this is minus 1, and that is plus 1. Now let's analyze how is the function or the derivative of this function changing on either side of these points, or the critical points. So we can take a test point, let us say minus 2 on this side. If I do minus 2, what do I see? If I put x as minus 2, then x squared is going to be positive, given and x squared minus 1 is going to be positive, right? Now, so if I'm testing for a point in this interval, which is minus infinity to minus 1, let us say that test point is, for me, minus 2, okay? Then this will be positive, so it is positive. If I plug in a point between, which is a fraction between 0 and minus 1, then this value will become lesser than 1, correct? Since it becomes lesser than 1 at this point, then what happens? So at this point we know it is increasing. So okay, at minus 2 what is happening? So this is x is minus 2. So this will make it negative. So it's not positive. It's actually negative at this point. So f dash x, what we're trying to analyze is f dash x. Okay. Now, if I put minus 2 here, then 8 times minus 2 is minus 16, and this part is positive. So it's negative overall, right? So we have negative here. If I put a fraction here between 0 to minus 1, let's say minus half. If I put minus half, what happens? This is negative, and this is also negative. So two negatives will make it positive, so in between it is going to be positive here. Right? So it is increasing in the interval of minus 1 to 0. Now if I have a value plus half, for example, then this is going to be negative, right? But this is going to be positive. So positive times negative is going to be negative. So I'll get negative here, correct? That is how the behavior of f dash is. Negative means decreasing, right? So interval of decreasing, and then if I put a value more than 1, let us say if I put a test point 2, in that case all will be positive and the function will be increasing. So we have our maximum and minimum points. So we have minimum, which seems to be the absolute minimum at minus 1. So we'll just write minimum here, and that is my maximum, and this is again minimum, right? So that's what I get. So I get my minimums and maximums, and minimum is at minus 1. So if I put minus 1 in my function, I get 0. So minimum is at 0. So we get here, let me write in a different ink, maximum and minimum points. So we get two minimums. So we have a minimum from this critical point analysis. So I'll actually draw the graph here. So I'm leaving the space open. We can write here. So we have minimum at these 2 points, which are at plus and minus 1, at x equals to plus and minus 1. And the y value we have seen, if I write plus and minus 1 here, y is 0. So y is 0. That is the minimum value. How about the maximum value? So the maximum value for us is at x equals to 0. So if I write x equals to 0, here I get 2. So the maximum value is y equals to 2. Do you see that? At x equals to 0, right? So that is the maximum value. So maximum is at x equals to 0. Okay, so you got maximum and minimum from f dash x. Now let's do the second derivative and find point of inflection. So let's do second derivative. So let's write second derivative. Second derivative of the function should be what? Where is the first derivative? Here is the first derivative, so second derivative will be derivative of this. 8 times 3 is 24, so write 24x squared, and this is just the number 8. You can take 8 common this time, and you get 8 times 3, so 3x squared minus 1. And when is this equal to 0? This is equal to 0 at x equals to 1 over square root 3, correct? So here we get a critical point, and that critical point for us is at x equals to 1 over square root of 3, right? Plus and minus, because this is square. That is our critical number. Now let's analyze that one, which is right here. So let me this time give some space between, well, technically what I'll do is 1 over square root 3 is going to come between these values, so I'll write a value here. So let me squeeze it in as I did. So we did a mistake already of taking these points too close. Anyway, it doesn't affect our solution. It's kind of good. So we get here minus 1 over square root 3, and this is plus 1 over square root 3. I hope you can see the page. Let me just push it a bit further. Okay, so these are our 2 points where we are trying to check concavity, right? So here the idea is we'll check concavity. So when do you have a point of inflection? If concavity changes at these points, you have point of inflection. And how do we decide about concavity? Second derivative is positive, that means concave up. Second derivative negative means concave down, right? So let's have some test points and see for ourselves. what is the real value of double derivative, second derivative. So if I have a value, let us say 0, that's the easy way to put. If I take 0 as my value, then what do I get? For 0, as you can see, it is going to be minus 1, right, times 8, a negative value. That means here it is going to be concave down, right, negative value. So let me write first a negative value like this, negative value, and so we know our function at this particular time in between these two should be concave down, right? So kind of like this. Do you see that? Kind of like this. Okay. Now if I take a value which is more than this, that means let me take a value 1 here on this side and minus 1 on this side. So if I put 1 here, so 3 is greater than 1, I get positive. Even with minus 1, x square will make it positive. So both are positive for us. So in these intervals, we have concave up, right? So we have concave down between minus square root 1 over 3 and between 1 over square root 3, but concave up from these points to infinity. From minus infinity to minus 1 over concave. That means we do have point of inflection, right? So these 2 points for us are actually point of inflections, right? So these are point of inflections at x equals to plus minus 1 over square root 3. With all this, we are in a good position to sketch our graph. Now let's just sketch it, right? So we have y-axis. Now let me say this is my y-axis, and hurriedly let's sketch our graph. So we have maximum at 0, 2. So that is our maximum, and we can see it just curves like this at maximum, correct? And we have point of inflection as 1 over minus square root 3 and 1 over plus square root 3. That means the graph actually goes like this. Do you see that? It goes like this. And these are my point of inflections, right? Correct. Where the concavity change, I think you can see that. Concavity is concave down and then concave up all the way. Concave down in the center and concave up all the way. Do you see that? And these are the point of inflections which you're talking about. So that is how calculus helps to make our graphs more accurate. So we were not finding point of inflections when we did sketch the graph of polynomial functions earlier, but now we are in a position to pinpoint them. Do you see that? So we have a maximum here at 0 and the maximum value is 2, and we have 2 local minimums which are also absolute minimums which are at plus and minus 1, and point of inflection is at plus and minus 1 over square root 3. That completes my work, and I hope you have understood the aspect of curve sketching with this. Remember one thing, whenever we are doing curve sketching, we are seeing it right from the type of polynomial we have in hand. We know it's a polynomial, so we have to draw a smooth curve, right? And then all these behaviors are very important so that we can accurately graph our polynomials. Follow this method and then sketch your polynomials. Thank you and all the best.